Welcome to section 11.7, events involving and conditional probability. Objective number 1, find the probability of one event and a second event occurring. When we want to find the probability that event A and event B both occur, we need to determine whether the events are independent or dependent. This determines which formula we use. Independent events are events where the occurrence of one event does not affect the probability of the other event occurring. Examples of independent events include flipping a coin twice because the first flip doesn't affect the second flip, rolling two dice, one dice result doesn't affect the other, drawing a card, replacing it, and then drawing it again. Replacement here makes them independent because you restart with all of your cards. Rainy today and rain next week are generally independent. When you rain on Tuesday, it doesn't affect you raining the following Tuesday. So the key phrase to listen for when identifying independence is with replacement, because that usually indicates independence. So if A and B are independent events, then the probability of A and B equals P of A times P of E. In other words, when events are independent, multiply their individual probabilities. This can be extended to more than two events. So if we have the probability of A and B and C, this would be the probability of A times the probability of B times the probability of C. For example, when a fair coin is tossed 2 times, what is the probability of getting tails in the first toss and heads on the second toss? Well, there are 2 methods that we can take to solving this problem. The first method would be to list all of the outcomes. Well, we know when we flip a coin, we can either get heads or we can either get tails. So let's list all of the 2 set combinations that we can get when flipping the coin twice. So our sample space is going to be the list of all of our outcomes. So we can get heads, 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 tails, tails, heads, or tails, tails. Now our problem is finding the probability that we get tails the first toss and heads the second toss. So we only have one favorable outcome in our sample space that matches that, and that's tails, heads. And that favorable outcome is 1 out of the 4 possible options. So the probability that we get tails and then heads is 1/4. Our second method is to use the multiplication rule. The 2 tosses are independent. The first toss doesn't affect the second because I get to restart with all of my potential results. So the probability of tails on the first is 1 out of 2. And then for the second, heads is also 1 out of 2. So the probability of tails times heads is going to be the probability of tails times the probability of heads. So that's 1/2 times 1/2, which equals 1/4. Therefore, the probability is 1/4 or 25%. Now, suppose a jar contains 4 white, 3 red, and 3 blue marbles. Okay, so that's a total of 10 marbles. 1 marble is selected at random, then replaced back in the jar before another marble is selected. Find the probability that a red marble is selected on 2 consecutive selections. So because the first marble is replaced, the 2 selections are independent events. So the jar has the same marbles each time. So the probability of getting red on the first selection is going to be 3 out of 10 because I have 3 marbles that are red. The probability of getting red on the second selection is also going to be 3 out of 10. And this is because I have replacement, meaning we're putting my selection back into the jar. So the probability of red and red is going to be the probability of red times the probability of red, which is 3/10 times 3/10, which equals 9/100. Therefore, the probability of selecting a red marble on 2 consecutive selections with replacement is 9 divided by 100, or 9%. So we just finished working with independent events. Dependent events are events where the occurrence of one event does affect the probability of the other event occurring. Examples of dependent events are drawing 2 cards without replacement. So that means removing 1 card and not putting it back into the deck. So now that changes the deck in the second attempt. Selecting marbles without replacement. So again, removing the marbles and not putting them back changes what's left. And then choosing two people from a group for different positions, because we can't choose the same person twice. Once they're chosen, we have to choose somebody else. So the key phrase to listen for is without replacement, because that usually indicates dependence. So if A and B are dependent events, then the probability of A and B is going to equal the probability of A times the probability of B, given that A has occurred. This is often written as the probability of A and B equals the probability of A times the probability of B given A. In other words, we're multiplying the probability of the first event by the adjusted probability of the second event. And it's adjusted because the first event already occurred. For example, suppose we have a jar that contains 4 white, 3 red, and 3 blue marbles, the same as before, so we have a total of 10. One marble is selected at random and now does not get replaced before another marble is selected. Find the probability that a red marble is selected on 2 consecutive selections. So we have to remember here that because the first marble is not replaced, the 2 selections are dependent events. After removing one marble, there are now fewer marbles in the jar. So for our first selection, the probability red on our first selection is going to be 3 out of 10. Now on the second selection, given first selection was red, we now have 2 red marbles left for a total of 9 marbles in the jar. So if we want to select red for the second selection, given that we've already selected a red, we're now going to have 2 out of 9 as the probability of getting red for our second selection. So the probability now of getting red on 2 consecutive selections is now going to be 3 over 10 times 2 ninths, which gets us 1/15th or 6.7%. Okay. Notice that this is lower than the replacement, which was 9%, because removing a red marble makes it harder to select another red marble. All right, let's do an example together. So, if the probability that South Florida will be hit by a hurricane in any single year is 5/19, what is the probability that South Florida will be hit by a hurricane in 4 consecutive years? What's the probability that it will not be hit by a hurricane in the next 4 years? And what is the probability that it will be hit by a hurricane at least once in the next 4 years? Okay. So for the first one, we know that the probability of South Florida being hit by a hurricane is 5/19. So the probability that South Florida will be hit in 4 consecutive years would be 5/19 times 5/19, because that's year 2. Year 3, the probability is 5/19. Year 4, the probability is 5/19. So this is 5/19 to the 4th power, which equals 0.0048. Now the probability that it will not be hit by a hurricane in the next 4 years. So we first need to find the probability that it won't be hit in a single year. Okay. So the probability of no hit would be 1 minus the probability of a hit. Well, we know the probability that it will be hit by a hurricane is 5/19. So the probability that it won't be hit is 4/19. So the probability that there will be no hit for 4 consecutive there we go, years would be 14 over 19 to the 4th power, which is 0.2948. Okay, because each year it's going to have the probability of 14 over 19. And the third one, what's the probability that South Florida will be hit by a hurricane at least once in the next 4 years? Okay, so at least here is going to be the complement of not being hit at all. Okay, so the probability of at least once in the next 4 years. So that will be 1 minus not being hit. In the next 4 years. So at least as the complement to no hit in 4 consecutive years. So this will equal 1 minus 0.2948, which will equal 0.7052. Okay, or 70.5%. All right, a single die is rolled twice. Find the probability of rolling a 2 the first time and a 3 the second time. Okay, so the probability of rolling a 2 is going to be 1 out of 6 because we have 6 sides. Each number is represented at one time. The probability of rolling a 3 is also 1/6. So the probability of rolling a 2 and a 3 will be 1/6 times 1/6, which is 1 over 36, or 0.0278. All right, we're back to South Florida. All right. So we want the probability that South Florida will be hit by a major hurricane, category 4 or 5, in a single year is 1/16. What's the probability that it will be hit by a major hurricane in 3 consecutive years? What's the probability that it will not be hit by a major hurricane in the next 10 years? And then what's the probability that South Florida will be hit by a hurricane at least once in the next 10 years? Okay, so why don't you pause and attempt this problem? All right, for the first one, we want the probability of being hit 3 consecutive years. So we should have did 1/16 to the third and gotten 0.000244. For the second, we want the probability that it will not be hit for the next 10 years. So the probability of no hit is going to be the complement of it being hit. So that's 15 over 16. So now the probability of no hit for 10 consecutive years would be 15 divided by 16, not 10, to the 10th power. And you should have gotten 0.5241. And then lastly, we want the probability of a hit at least once in the next 10 years. It's going to be the complement of no hit for 10 consecutive years. So that would be 1 minus 15 divided by 16 to the 10th. So 1 minus 0.5241, which equals 0.4759. All right. Objective 2, compute conditional probabilities. So conditional probability is the probability of an event occurring given that another event has already occurred. It answers the question, if we know event A happened, what's the probability that event B will happen? The key phrase is given that, or if we know that. So when we say given that A has occurred, we're essentially saying that we are restricting our sample space to only outcomes where A is true. We're recalculating the probability based on this smaller restricted sample space. For instance, if you roll a die and someone tells you the result is less than 4, you know the outcome must be 1, 2, or 3, not 1, 2, 3, 4, 5, 6. Your sample space has been restricted because you're only looking at results less than 4. The conditional probability of B given A is written as the probability of B given A. So the given is represented by the vertical line. And it equals the probability of A and B divided by the probability of A. In other words, the probability of B given A equals the probability of both A and B occurring divided by the probability of A occurring. An alternate approach is to restrict the sample space to the outcomes on which A occurs and then find the probability of B within that restricted space. So there are two ways to think about conditional probability. The first method is to restrict the sample space. So when we know event A has occurred, we only consider outcomes where A is true and then count the favorable outcomes within this restricted space. The second method is to use the formula. So we'll calculate the probability of A and B and the probability of A and then divide. Both methods give the same answer. So we just need to know we need to know when to use each formula, whichever one is easiest for the problem. So suppose you roll a 6-sided die. Find the probability of rolling 3 given that the outcome is a number less than 5. So we're looking for the probability that 3 given that the number is less than 5. So step 1, we are going to identify our restricted sample space. So given that the outcome is less than 5 means we only consider outcomes less than 5. So our sample space will be the numbers 1, 2, 3, and 4. So we have 4 numbers in our sample space. Next, we're going to count favorable outcomes within the restricted space. So then how many ways can we get 3 from our sample space? And 3 is only present one time, so the number of favorable outcomes is 1. Step 3, we're going to calculate the conditional probability. So the probability of rolling a 3, given that the number is less than 5, is going to now equal 1 over 4. Therefore, the probability of rolling a 3, given that the outcome is less than 5, is 25%. Okay. Now let's say you are dealt one card from a 52 card deck. Find the probability of getting a 9, given the card you were dealt is a black card. So now we're looking for the probability of selecting a 9, or I guess receiving a 9, given that it's a black card. So we'll identify the restricted sample space. So given the card is black means we only consider black cards, which are spades and clubs. So the restricted sample space is going to be 26 black cards. Step 2, we're now going to count the favorable outcomes within the restricted space. So how many 9s are black? Well, we have a 9 of spades and a 9 of clubs. So that means we have 2 cards that are black with the number 9. So to calculate the conditional probability, we would be taking 2 over 26, which is equal to 1/13. Therefore, the probability of getting a 9 given the card is black is 1/13. Okay. All right, so let's do an example together. So use this table below. Find the probability that a U.S. woman aged 40 to 49 has a positive mammogram given that she has breast cancer. And then find the probability that this woman, a U.S. woman, has breast cancer given that she has a positive mammogram. So we're trying to find two probabilities here. The first one, a mammogram, given breast cancer. Well, this is positive. Positive mammogram, given that they have breast cancer. And then we want to know the probability they have breast cancer given positive mammogram. Alrighty. So for the first one, we want a positive mammogram. So that's this row right here. Okay. And given that they have breast cancer. So that's this column right here. Okay. So that would be 720 people. Out of how many people? Well, the last demographic that we are given, so the people that we're looking at are going to be the people who have breast cancer. Given that they have breast cancer, how many of them had a positive mammogram? So breast cancer is the pool, it's the sample space that we're looking out of. And how many total people have breast cancer? 800. So this will equal 0.9. Okay. Now for the second one, we have breast cancer given a positive mammogram. So we're looking in the same row and column, but this time we're looking at breast cancer given that they had a positive mammogram. So now we're only looking in the group of people who have a positive mammogram. Okay. So the people who have a positive mammogram would be 7,664. How many of the people who have a positive mammogram had breast cancer? 720. And so that equals 0.0939. Let's do another one. So we're going to use the data in the table to find the probability of surviving a car accident, given that the driver wore a seatbelt, and then find the probability of wearing a seatbelt, given that the driver survived an accident. Okay, so the first one, they survived and wore seatbelts. And the second one, they wore a seatbelt given that they survived. All right, so driver survived is this row, wore a seatbelt is this row. All right, so the probability of surviving a car accident, given that the driver wore a seatbelt. So wore a seatbelt is the group that we're looking at. So the total is 412,878. Out of these people, how many of them survived a car accident? 412,368. Okay. That equals 0.99877. Now we're going to be looking at the probability of wearing a seatbelt given that the driver survived an accident. So how many total people survived an accident? 574,895. Of those people, how many wore a seatbelt? 412,368. That's 0.7173. All right. And that concludes section 11.7.